So today we're going to talk about electron configurations. Electron configuration shows the occupation of orbitals by electrons for a particular atom. So in short, it is basically a summary of how the electrons is put around the nucleus. For example, hydrogen, it is in 1s1. So 1s is called orbital, and number 1 here is the number of electron in orbital. So keep in mind that each orbital can hold a maximum of 2 electrons. So we have SPDF subshell. So for S subshell, it has only one orbital, which means it can only hold 2 electrons. P subshell, it has 3 orbitals, which means it can hold 6 electrons. D subshell has 5 orbitals, which means 2 times 5, it can hold 10 electrons. And then F subshell has 7 orbitals, can hold 14 electrons. This table basically showing which one is the S block elements, which one is the P, the D, and the F on the periodic table, and they're already color coded. So this is like the S, and then we have pink is the P orbital, and then the orangey is the D orbital, and the green is the F. This period's number is the energy level. Another way to look at it is using this table. So this is like the previous table. This is like the S, and then the P, the D, and then the F, and so on. So basically the energy level, if you look, is 1, 2, 3, 4, 5, 6, 7. So we have 1s, 2s, 2p, 3s, 3p, 4s. But for transition metal, the number has to be the energy levels minus 1. So instead of 4d, it has to be 3d, and then we've got 4p. 5f, so 5 minus 1 become 4, so it's 4d. So that's the exception. Alright, so to write an electron configuration for an element, first you have to find the atomic number, the same thing as proton. So this number is equal to the number of electrons in a neutral atom. Second is to use the order of filling, which I'm going to show you in a bit. And also, if you don't want to use the order of filling, you can also just reference the periodic table. Keep in mind, you have to remember this, that S can only have 2 electrons, P 6 electrons, D 10 electrons, and F 14 electrons. Okay, so this is the order of filling. We go from 1s, and then 2s, 2p, and then after 2p, 3s, and so on. So let's do some example. Let's see carbon. So based on the periodic table, carbon has 6 atomic number. In that case, we start from 1s. So we know that S can have 2 electrons, P can have 6 electrons, D can have 10 electrons, and F can have 14 electrons. So that means in 1s, we can do 1s2 and then 2s2. So right now we have 2 plus 2, 4 electrons. We need 2 more. So that means we can put another 2 in 2p2. So right now we have 6 electrons, which is the electron of carbon. And then our order of filling, 1s, 2s, 2p. Let's do some more example. Let's say it's chlorine, which is 17. If we do the same way, we would have 1s2 because S can have 2 electrons, and then 2s2, and then go to 2p6. So if we stop here, we have only 10 electrons, 2, 2, 6, which is 10, but we need 17. So after 2p, it is 3s. So 3s, but S can put only 2, so 3s2. So right now we have 12. We need 5 more, and then after 3s, there's 3p. So P can put 6 electrons. We need only 5 more, so we can do 3p5. And if you add the number up, it should give you 17. So another example, manganese. So manganese has 25 atomic number. So we would do the same thing. We would start with 1s. So we have 1s2, and then 2s2, 2p6, because P can put 6 electrons. And since we want 25 electrons, we have to keep going. So and then we have 3s2 and then 3p6. So if you stop here, you have 18. So we need to keep going. So after 3p, there is a 4s before we go back to 3d. So 3p, 4s, so we have 4s2, and then it's going to be 3d. But right now, if we count 2, 4, 10, 18, 20, so since d can put 10 and we need only 5 more, we can just put 3d5. And then when you add all the these number up, it should give you 25 electrons. Okay, so this is how you do electron configuration based on the order of filling. However, like in an exam or quiz, you are not going to be given this order of filling. So your choice is either you remember it or use the periodic table, which I'm going to show you in a bit. So we know that the blue is the S, the pink is the P, orange is the D, and the green is the F. So for example, if you want to do like fluorine, so fluorine is here. So it has 9 atomic number. So what you would do, you know that this is the energy level. So you would have 1 S2 because the helium is supposed to be here. So 1 S2, and then you would have 2 S2, and then after 2 S2 you would have 2 P because the pink is the P. And then how many P? 1, 2, 3, 4, 5. 2 P5. And then if you add the number up, it should give you 9, which is the atomic number of fluorine. Okay, let's do another example. Let's do selenium. Selenium has an atomic number of 34. So we would always start with 1s. So 1s, we would have 1s2, and then 2s2. After 2s2, we have 2p6 because selenium is 34, it's right here. So right now we pass 10 electron. After 2p6, we would go back to 3s. So we have 3s2, and then we would have 3p again, so 3p6. So after 3p, we go down to 4s2. However, if you remember the transition metal, it's not going to follow the energy level like the other main group. So instead it would be 4 minus 1. So it would be 3D and then 3D10, because if you count this orange block, it's like 10, and we also know that D can put 10 electron. And then after 3D10, we go back to 4P. So how many P? Selenium is right here, so 1, 2, 3, 4. So 4P4. So that's how you do electron configuration based on the periodic table. This periodic table is kind of confusing because it gives you also the 1s1, 1s2 and stuff like that. But like usually we don't have this type of periodic table. We use this type of periodic table instead. But even if you use this, you would be able to figure out the same answer as long as you remember that these 2 is the S, these 6 block is the P, these 10 is the D, and then there will be another 14 which is the F here, but this periodic table doesn't show it. And using periodic table, it is helpful because it tells you that the P has 6 electrons, the D has 10, the S has 2, and the F has 14. Okay, so let's move on to noble gas abbreviation. When writing electron configuration for element beyond neon or beyond any other noble gas, the electron configuration of the previous noble gas is often abbreviated by the symbol for the noble gas in brackets. So the definition is kind of confusing, but just keep in mind that if you write of electron configuration for an element that is beyond neon, so basically starting from sodium you can do noble gas abbreviation. So let's do one example. Let's do magnesium. My full electron configuration, if you look at your periodic table, you can do it with me. So we have 1s2, 2s2, 2p6, and then 3s2. And then if we count these numbers, it would give me 12, and magnesium atomic number is 12. So I know my electron configuration is right. So since magnesium is an element beyond neon, so I can do noble gas abbreviated by putting neon. So neon has an atomic number of 10. From here, I already symbolize 10 electrons, so I only need to write down 2 more, which means I can just write 3s2 because these 10 electrons represent neon already. Let's do another example. Let's do bromine. So for electron configuration, you would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we get 2d. It has to be the energy level -1. So 4 minus 1, 3. So 3d, and since bromine is 35 atomic number, we have to go past all of the d blocks, so 3d10, and then we would go back to 4p5. So if you count the number, it would give you 35. And then my abbreviated noble gas, we wanted the noble gas to be as close to the element as possible. In this case, instead of using neon, I can use argon. So argon, and argon is 18 electrons, so that means these 18 electron is already used in argon. That means I can just write whatever remains. So 4s2, 3d10, and then 4p5. So that's how we write noble gas abbreviation. Orbitals diagram. So orbitals diagram is another way to represent the summary of electrons in an orbital around the nucleus. However, it is going to be written as a box. So for example, hydrogen is going to be a box and then one S with an arrow like this. So this box represents the 1s orbital, and this arrow right here is represent the electron in the 1s orbital. So electron in 1s orbital. So in orbital diagrams, the direction of the arrow, like this arrow, pointing up or pointing down, so up or down, represents the electron spin. So all electrons have electron spin. So the Pauli exclusion principle said that orbitals may hold no more than 2 electrons with opposing spins. So what that means is that it could only have these and that, like one up and one down in one orbital. Another rule for orbital diagram, the Hund's rule. When filling orbitals with equal energy, like what this means is like the same energy level, electrons fill them singly first with parallel spin. So for example, nitrogen, electron configuration of nitrogen, we would have 1s2, 2s2, and 2p3. So if I wanted to write as an orbital diagram, I would do one box because each box represents one orbital, and S have one orbital, and then another for 2s, so 1s, 2s, and P has 3 orbitals, so it has to be 3 box like this. So the way we fill it up, 1, 2, 1s orbital filled, 1, 2, 2s orbital filled. So for P, we do 1, 1, and 1, like that. We don't do it like this, 1, 2, 3. This is not the right way to fill the 2p orbital. It has to fill singly first with parallel spin. We also don't do it like this. No. that's not right. It has to be parallel. Okay, so let's do an example. Write a full electron configuration, noble gas separated, and orbital diagram of sulfur. And then write electron configuration of sulfur ion or sulfide. So you can use the order of filling or you can use the periodic table. But since I don't want to remember the order of filling and my professor is not going to give me that in the exam, I prefer using the periodic table. So if you look at the periodic table, we know that sulfur has a 16 atomic number and it's right here. So we know these two is the S block, this is the P block, and this is the D block. So now we can start writing. So sulfur, we can do 1s2 and then 2s2, 2p6, 3s2, and then sulfur is right here, so we're going to get 3p1, 3p2, 3p3, 3p4. So we will have 3p4. Since sulfur is close to neon, the noble gas is going to be neon. So neon, and then since neon has 10, so it's basically take 10 electron away, so it's going to take this electron away. So now what remain is 3s2, 3p4, and if you add up these number, it should give you 16, which is the atomic number of sulfur. So orbital diagram, we know that S only has one orbital, that means it has only one box, 1s, 2s, and then P has 3 orbitals, so it has 3 boxes, 2p, 3s, and then we would have 3p right here. So filling them in, 1 2 1 2 1 2 3 4 5 6 1 2 1 2 3 4. So singly and parallel first. So that's done with part A. Part B, write electron configuration of sulfur ion or sulfide. So we know this has a 2 minus, which means that the electron is going to be the atomic number of sulfur. So 16 minus 2 equal 18 electron. So we have to add 2 more. So the formula to find the ion electron is number of atomic minus number of charge. Or you can just look at the ion's charge and figure out that if it's a minus, you need to add. If it's a plus, you need to minus it. In this case, electron configuration of S2 minus, it would be the same thing as sulfur, but we add 2 electrons. So those 2 electrons going to be added to the P, because remember the P needs 6 electrons, but right now we have only 4. 1s2, 2s2, 2p6, 3s2, 3p6. So basically for ions, they want to lose or gain electron because they want to have like a filled orbital, or they want it to become more like a noble gas. In this case, sulfide has a filled orbital. Every orbital got filled, and then if you look at these carefully, you would see that this is the electron configuration of an argon. Okay, so let's do another example. Write a full electron configuration, noble gas abbreviated, and orbital diagram of calcium, and then indicate whether it is paramagnetic or diamagnetic, and then write electron configuration of calcium 2+. We know that calcium has an atomic number 20, and it's right here. So we can start writing calcium equal to 1s2. After 1s2 we have 2s2. 2s2 we have 2p6, and then 3s2, 3p6. And if you add a number up, it still has 18 electrons, so we need 2 more electrons. And then if you look at the periodic table, calcium is right here, so we need 4s2. And if you add them up, it's going to give you 20. Noble gas abbreviated, calcium is close to argon, So we can say argon, and then argon takes 18 electrons, so there's only 2 more, so it's argon to take all of these, so what remains is 4s2. So that is the noble gas abbreviated. Orbital diagram. S only have 1 orbital, that means it has only 1 box. So I would have 1s, 2s, 2p, 3s, 3p, and then 4s, and then started filling. So this is the orbital diagram of calcium. Everything is filled. Okay, so is this paramagnetic or diamagnetic? So paramagnetic means that it has unpaired electron. So unpaired electron, while diamagnetic is paired electron. So if you look at all of the orbital, everything is paired, like all of the electron is paired, which means that calcium is diamagnetic. How about sulfur? So if you look at sulfur, you have 2 unpaired electrons, which means that for sulfur, it is going to be paramagnetic. How about electron configuration of calcium 2+? You know that whenever there is an ion with a plus charge, we know that it's going to lose electron. So there are ways you can find the number of electron. You can do atomic number minus number of charge. In this case, atomic number is 20 minus plus 2, so it's going to be 18 electron. So you lose 2 electron. Or another way to think of this is that since you have a plus charge, you know you lose electron. So 2 plus means you lose 2 electron. So calcium 2+, it's going to be similar to the electron configuration of calcium, but we're going to lose 2 electrons, and we're going to lose it from the highest energy level, which is the 4s level. So since 4s has 2, so we lose 2 from there. So we would get 1s2, 2s2, 2p6, 3s2, 3p6. And you can write 4 as 0, but that's not necessary. Usually we don't write it, so 3p6. So that's the electron configuration of calcium 2+. Okay, so another example, write a full electron configuration of iron 2+, and iron 3+. You can pause for a minute and then try this yourself. So like the example we just did so far, iron is right here, so we can start doing our electron configuration. Fe, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So since this is a transition metal, the D block is not going to start with number 4, but it's going to be 4 minus 1. Like we already mentioned earlier in the video, even though it is at the 4 energy level for transition metal, it has to be 4 minus 1. So we've got 3D, and iron is here, so it's going to be 1, 2, 3, 4, 5, 6. 3d6. So that is the electron configuration of iron, and if you add the number up, it's going to give you 26. So how about iron 2+? So we're going to remove 2 electrons, but from where? Like I said, we have to remove 2 electrons from the highest energy level first. In this case, transition metal, we have to remove it from the 4s first. So we have to remove it from these 2 electrons first. So right now we would have 1s2, 2s2, 2p6, 3s2, 3p6. You can write it 4 as 0, or you don't need to, and then 3d6. Normally you don't need to write 4 as 0, but I wanted to show you that. How about Fe3+? So for iron 3+, we have to remove 3 electrons. So since we already removed 2 electrons from the 4s, we have to remove 1 more electron from the 3D because it is the highest energy level after 4s. So now we would remove from 3D, so 3D is going to lose 1. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. In this case, I remove one electron from the Fe2+, since I already done the Fe2+. But if you did not have iron 2+, you can just remove from the iron. Like I said, we remove 2 from the S, and then we remove 1 more from the 3D. So we're going to get 3D5. Exception to transition metal. So there are exceptions to transition metal, and those include chromium, molybdenum, copper, silver, and gold. Okay, so let's take a moment and write the electron configuration of chromium and copper. So if you write the electron configuration of chromium and copper without knowing that these guys are exception, I'm sure that we all going to get these electron configuration like I show right here. However, this is not the right electron configuration to write these guys. So the right electron configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then 3d5. And then the right electron configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. So the reasons why these exceptions occur is because a half-filled D subshell and a completely filled D subshell are very stable. So if you remember, D has 10 electrons in its orbital. So the half-filled D subshell means that D has 5. And completely filled D means that D has 10 electrons. So whenever you see these elements, you have to remember that they are exception and they want to have a half-filled and a completely filled, because it will make them really stable. So let's try an example. So write a full electron configuration of silver and silver ion. Take a few minutes and try this yourself, and then we can compare the answer. So if you look at the periodic table, like I said, you can use the order of filling or the periodic table. So periodic table, silver is right here. That means electron configuration of silver is going to be starting from 1s2. So 1s2, and then we've got 2s2, and then 2s2, 2p6, 3s2. After 3s2, there's 3p6. After 3p6, we have 4s2. And then after 4s2, we have D blocks. In this case, it's going to be 3D because 4 minus 1 is 3. And that's also another exception you have to remember. So 3D, since silver is right here, that means this is going to go past the D block, so 3D10. And then after 3D10, we have 4P6, and then 5S2, and then 4D, and silver is right here, so D9. However, since silver is an exception, we're going to write it as 5S1, 4D10. This is the right electron configuration of silver. How about silver ion? So for silver ion, we know we have to lose one electron because it has a plus charge. In this case, we have to lose from the highest energy as possible. So the highest energy is the 5s1. So losing one electron, we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then you can do 5 as 0, or you don't have to, and then 4d10. So this is the right electron configuration of silver and silver plus. Next, valence electrons. Valence electrons are the electrons in the outermost principal shell or the outermost energy level. These electrons are important because they are involved in chemical bonding. So let's take a look at silicon. So electron configuration of silicon is 1s2, 2s2, 2p6, 3s2, and 3p2. So valence electron is the outermost energy level. In this case, the valence electron of silicon is 3s2 and 3p2, which means that the valence electron is going to be equal to 4. 2 plus 2 equal 4. And then the rest of these is called core electron. So core electrons are the electrons that are in the innermost principal shell. And then valence electron are the electrons that are in the outermost principal shell. The elements within a column or a family all have the same number of valence electrons with similar outer configurations except helium. If you look at this periodic table, so group 1a, that means hydrogen, lithium, sodium, potassium, all of them has valence electron of 1. It's the same with group 2a. And then 3a, 4a, 5a all have 3 valence electron, 4 valence electron, 5 valence electron. Oxygen has 6 valence electron, fluorine has 7 valence electron, and so on. So the group number represents the valence electron of the element within the same family or column. So how about the valence electron of transition metal? So for valence electron of transition metal, it's kind of complicated and tricky. If we think that the valence electron is the electrons that is in the outermost energy level, which means that the valence electron of transition metal is going to be either 1 or 2. So we count it from like the 4s2, 5s2, 3s, and 7s without caring about like the d block. However, if you look at it based on how it involved in the chemical bonding, the valence electron is going to be both the S and the D. So we can say that manganese can either have a 2 valence electron or it can have 7 valence electron if it's involved in chemical bonding. The same with chromium. It can have 1 valence electron or it can have 6 valence electron if it's involved in chemical bonding, like the oxidation state. However, since electrons are really important in chemical bonding, we tend to believe that the 3 D blocks, like the first row of the D block, from scandium to zinc, they will have the valence electron of 4s and 3d. So that's just like a generalized idea. There wasn't really anything certain about the valence electron of transition metal. Like I said, it could either have the outermost energy level as their valence electron, or it can have both the S and the D valence electron. Okay, so let's do one last example. Write an electron configuration, noble gas abbreviation, orbital diagram of iota. B. Indicate whether it is paramagnetic or diamagnetic. C. Find the valence electrons and covalent electrons. So do this yourself and then we will compare the answer in a bit. Okay, so iodine is right here. It has 53 atomic number. Iodine, it will have 1s2. After 1s2 we have 2s2 and then 2p6. After 2p we have 3s2. After 3s2 we have 3p, 3p6, and then 4s2, and then 3d10, 4p6, and then we go back to 5s2, 4d10, and then 5p5. So that is the electron configuration. And then if you add the number up, you will get 53 as the same as the atomic number, which means that you have a right electron configuration. Noble gas abbreviated. So since iodine is close to krypton, we can use krypton. instead of argon and neon because that's so far. So krypton, and then krypton take away 36 electron. That means you can like count 10, 20, 30, 36. So right now we have got 5s2, 4d 10, and then 5p5, and then if you add all of them up, it should give you 53. So 36 plus 12 is going to be 48. 48 plus 5, 53. And then orbital diagram. So remember, S has only one orbital, so it means that it has one box. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then 5s, 4d, 5p. So now we start filling them. So singly and parallel first. So singly, parallel, then 4, 5. So is this paramagnetic or diamagnetic? Since we have one unpaired electron, it's going to be paramagnetic. And find the valence electrons and covalent electron. So you can look at the group number. Iodine is here, so valence electron would be 7. But you can also look at the highest, the outermost energy, the outermost energy level. So we have 5s and 5p, which means we also have 7th valence electron. And then the rest of them will be our covalent electrons. So 53 minus 7 will be 46. So we have 46 covalent electrons. So that's it about electron configuration, and I hope it's helpful. If you have any questions, just let me know. And this takes a lot of practice, so don't be discouraged because you cannot do it at your first try. I remember when I first started doing this, I also was very confused, but practice makes perfect, and don't compare yourself with others. Your progress is your progress, okay? Bye.